Okay, so this unit has been on applications of derivatives, and in this lesson we're going to look at an application of the derivative that is more analytical. So it's going to allow us to figure out some properties of these math objects, in this case limits, rather than contextual. So we're not going to deal with real life problems here. We're going to deal with some kind of abstract mathematical problems. So we talked about limits earlier this year. You guys also learned about them in pre-calc. This limit, you actually don't need any real calculus to figure out. This you could treat as just like a rational function, and you'd know because our degrees are the same, we would know that this is 3 over 2, right? So we don't need this rule to solve this problem. We can do it kind of analytically, but we're going to use this to demonstrate the rule, and then we're going to look at a problem where we need this rule in order to solve it. We can't solve it by our old methods. So this rule is called L'Hopital's rule, is how you say that. I'm sure that you guys will come up with a lot of different creative ways to say that word, but that's L'Hopital. He was a French guy. He actually stole this rule from somebody else, but it is named after him. And what it is a technique for finding indeterminate limits. So indeterminate limits are limits that result in these two cases. So when we get an infinity over an infinity situation, which is what we have here, right? So both the numerator and the denominator grow to infinity, or we get a 0 over 0 situation. We'll see one of those in a second. So these two statements, or these two fractions, I guess, don't really make a whole lot of sense. So remember, the reason that we think that this limit is 3 over 2, right, is because the top grows just a little bit faster than the bottom, right? And that's why if this exponent were higher, we would think that the limit would be infinity, right, because the top grows much faster than the bottom. Okay. The reason we call these indeterminate means we can't figure them out, right? These are indeterminate because it's unclear. In this case, it's unclear which infinity is bigger. So infinity is always like the biggest number we can possibly conceive of, but some infinities are bigger than others. For example, we know that x squared versus x to the third. X to the third has a faster growth rate than x squared does, right? So we know that this will grow faster than this. So we'd say like this is sort of a bigger, approaches infinity more quickly than x squared does, right? So when in this case, it's clear which infinity is bigger, but in other cases it won't be. And then 0 over 0 is also a weird case where it's unclear what's happening with the value of the fraction. So generally when we think when the bottom of a fraction approaches 0, that fraction gets really large, right? But we think when the top of a fraction approaches 0, that fraction is just approaching 0, right? So these two things kind of fight with each other to determine the value that the whole function is approaching. Okay, so let's take a look at our rule now. So if we have one of the following two cases, this is super important. This only applies in certain situations, right? So only when we get a result that's 0 over 0 or infinity over infinity. Then what it says is the limit of the quotient is the same as the limit of their derivatives. Okay, so let's see what that looks like here. So I would say, first of all, I would say that to justify it, the limit of as x goes to infinity of the top is infinity, and the limit as x goes to infinity of the bottom is infinity, right? So this tells me that it's an indeterminate form. So what I'm doing here is I'm proving that L'Hopital applies, right? Then I can say that my limit here is equal to the limit as x goes to infinity, and then I'm just going to power rule top and bottom. So this is not quotient rule, right? I'm taking the derivatives separately. So we get 6x minus 2, and then 4x on the bottom. And notice we still have an indeterminate form. We still have infinity over infinity. So I would do it again. Equals the limit as x goes to infinity of the derivative of the top is 6, the derivative of the bottom is 4. which is just 3 over 2. Okay. Like I said, we didn't need this rule to solve this problem, but that's how we do it. So essentially, we show that the theorem applies, which is what we did here. Then we take the derivative of the numerator and the denominator, and then try to take the limit again. And we can do it as many times as we need to. Okay. Let's look at another one. So here, this is an example of a limit we could not find algebraically because it's, well, there's nothing we can cancel out, right? There's no way to simplify this, right? Even if we get real creative with our algebra. So we could not have solved this limit before this point. And notice the limit of the top. Cosine of 0 is 1. 1 minus 1 is 0. So the limit of the top is 0. The limit of the bottom is obviously 0. Right, so this is an indeterminate form. So L'Hopital applies. So I know that my original limit, and often, I think this is good, teachers write, or students write LH over the equal sign to make it clear what they're doing. I think that's a good move. So I'm going to take the derivative of the top and the bottom separately. So the derivative of cosine is negative sine, and then the derivative of negative 1 is 0. And then on the bottom, I get 2x minus 1 when I take the derivative. Okay, now, sine of 0 on top is 0, but on the bottom now, 2 times 0 minus 1 is negative 1. So notice I don't have an indeterminate form anymore. So I have 0 over negative 1, which is just 0. Okay. So that is L'Hopital's rule. So that made it very easy to solve this limit that would have been impossible before. So you're going to start with some easier ones on formative this time, and then we have some harder applications on delta math coming up.